Hey there, and welcome to a course on the Introduction to Math and Mathematics for Financial Engineering. My name is Aditya Diwakar. I'll be teaching the class over the next few weeks. I'm a student at the Georgia Institute of Technology, and a little bit about me is I've been into financial markets and financial derivatives for the past few years, specifically the math part of them for about the last 6 to 9 months. And I've been handling markets like the New York Mercantile Exchange for natural gas. And I also have a pretty large presence in trading crude oil and Brent oil, also on the New York Mercantile Exchange. So it's just a little bit of a hobby of mine. And over the past few months and past few years, I've been understanding the mathematics behind financial engineering. So I want to go ahead and teach you guys the introductory and the preliminary mathematics for understanding these financial engineering topics. So throughout the entire course, we'll be focusing mostly on pure math, which is then applied. So a lot of these lectures are going to be, we'll have some bit of pure mathematics, formulas, proofs, etc., stuff like that. And then we'll be applying those to financial situations and financial contexts, which will give them, hopefully you'll be able to understand the applications of those mathematics. So over the course of the semester, or of the course of the course of the class, we'll be discussing things like bond yields. We'll be talking about options in the money, out the money, and out of the money. We'll be also understanding the implied volatility and also the Greek variables in mathematics behind those Greek variables. And for this class, we're not requiring much as a prerequisite. The only prerequisites I would suggest is a little bit of introduction to into linear algebra. So and also an introduction to multivariable calculus. So for linear algebra, we're not going to require much. We're only going to need, the understanding of determinants and the understanding of a few complicated topics like diagonalization. Diagonalization may or may not be discussed. We'll see as the course progresses. And then further, we'll be talking about, for the sake of multivariable calculus, we'll be discussing double or triple integrals, and then also, the manipulation of bounds on those double and triple integrals. But other than that, and in terms of financial prerequisites, we're not going to require much, although it is good if you have an understanding of the share market in general, and then also options in general, puts and calls, and how they work to a very bare extent. I have no problem with going over those topics when we reach into those applications. But generally, when when we're discussing the Black-Scholes model, we should have some understanding of what puts and calls are, and then obviously when we do calculations on spreads and calculations among using Greek variables, we want to understand what those means. But I'll introduce those Greek variables as this course progresses as well. So our first topic is going to be very trivial, and this entire lecture, this lecture today, is also going to be very mathematical with no application to finance. Our application to finance will actually come at a later date, potentially into the second half of the next lecture, or potentially even the third lecture, before we start introducing. My plan for this course is to introduce about half a chapter or so per lecture, but that may vary depending on the length of the chapter and the content and the diversity of content. I would like to cover all similar topics in one day or in one lecture, but sometimes if it's too long, I will split them out. And if the topics are very they don't have any similarities, then I'll also split those up into multiple days. So our first topic we're going to be talking about is something that's very trivial and has been discussed, in previous math classes that you may have taken. And those are going to be the even and odd functions. So an even function and odd function, once again, they're extremely trivial, but they are important to understand and to know. So what we'll do is we'll just define an even function. So an even function can be defined simply by f of x equals f of negative x. So any function, so for some function f of x, if you apply the negative parameter rather than the positive parameter, you will get the same value regardless. So an example of this is I'll define as a g of x, and I can just define that as x squared, and then we can prove that this is an even function, and we'll do this proof by saying the parameter is negative x instead. So negative x is just negative x squared, which is just x squared. So this is proving that regardless of the sign of the parameter, as long as this value x is the same, irrespective of the sign, we'll get the same value, x squared in this case. And if I want to make a chart of this, you can just show this is x squared. This is y equals x squared. And then for any point, let's say, 3 here, the value is going to be, or sorry, this is -3. So the value at -3 is going to be 9. And then likewise, on the other side, right here, this will be the value of the x value of 3. So we'll get a y value. The function will return a value simply of 9, right? And I hope that makes sense. So that's an even function, and they're pretty simple. Now we'll move on to an odd function. So an odd function is similar to some extent. So for any function f of x, when we input the negative parameters, so if the sign is changed, we'll simply get the negative value of the function. So I'll give you an example for this. So g of x equals, let's just say x, okay? And with g of x being equal to x, now if we want to have g of negative x, we'll just simply get g of negative x equals negative x. And we'll notice that negative g of x is equal to the same thing as a g of negative x. So this would be an odd function. And so a chart of this is pretty simple as well. So this line here, y equals x is our function. And that for any value, let's say here we're doing -3, and here we're doing 3. So this value here will just be x, so it's 3. And this value here is also just x, which is -3 comma -3 for the coordinate there. So I hope that makes sense. There's a symmetry in both of these examples. The symmetry in this case will just be x equals 0 or the y-axis. And then the symmetry here will just be y equals negative x, which is like that. And I messed up that line, but the point is there's a line of symmetry on y equals negative x. So that's a pretty basic understanding, and these are obviously very, very simple topics. And then one more complicated topic we can talk about is the properties for integration. So once again, these are actually very, very simple functions, simple topics, but they have some interesting properties when you're considering the integration of these functions. So the integration, when you're taking the integral for, let's say, an even function, we can notice that if we want to take the integral from, let's just say, -3, and I'll actually just write it as a general, so let's just say negative a to 0, actually, of f of x dx. So, let's just say it's actually g of x in this case. So for g of x, this integral from negative a to 0, with a being 3, is just going to be this integral here, this section of the curve, right, this section under the curve, here bounded by this line x equals -3, this function x squared, and obviously the x-axis is y equals 0. And we'll notice that this integral is actually equivalent to the integral from 0 to a. So, this graph is a little bit messed up, but simply, this is going to be equal to the integral from 0 to a, f of x dx. Okay? So essentially saying so that it shows the symmetry that any integral from from -a to 0 is going to be the same integral from 0 to a, and that's simply because of the symmetry. And then we can also show if we want to take the integral from, and this is the case for even. Let me write that there. Yeah, so that's the case for the even functions. So now if we want to take the integral from -a to a of this function, of any function, f of x, well, we can simply add these two, because when we add integrals, when we add integrals of the same function with different bounds, we simply will add the bounds together. So when we're doing -a to a, that's the same thing as saying -a to 0 plus 0 to a. Well, since these are equivalent, we can actually just pick one and multiply by 2. So we'll have 2, and then -a to a, or sorry, my bad. We'll have 2, 0 to a of f of x dx. And similarly, you could have picked -a to 0 instead. So that should give you a quick understanding of the even functions. And for the odd functions, we'll notice there's a similar principle. And if I just erase this diagonal line that's going across here, Well, we'll notice that the integral from 0 to a is simply going to be, and a being 3, is simply going to be this area here, this triangle here. And similarly, this integral here will be the integral from negative a to 0. Well, we'll notice, since these are actually basically opposites of each other, where this value is 3 and this value is negative 3, when we're taking the integral from here to here and the integral from here to here, or 0 to negative 3 to 0 and 0 to 3, they're actually equivalent if you take the absolute value of the value, or if you take the absolute value, okay? So this area here, so not talking about the integral, but the area instead, this area is equivalent to the area there. So what this means in other words is that since this is the negative, this is negative 3 to 0 is the negative integral of 0 to 3. So we can write that as negative a to 0 of f of x dx is the same thing as the negative integral from 0 to a of f of x dx. And likewise, we have another example like this, when we're integrating from negative a to a of our function f of x dx. Well, that is going to be the sum of these two terms. Well, the sum of these two terms is simply going to be 0. And that also makes sense intuitively that for any integral, or for any very, very tiny rectangle in this region from negative 3 to 0, there's going to be that same size but opposite sign, very, very tiny rectangle in this region from 0 to 3. So over the entire bound, those rectangles will cancel out, and the integrals will cancel out. So you're just going to be left with the integral of 0. Whereas this area would simply be, 2 times the area is here. But since we're calculating integral, they'll actually be canceling out. So those are some pretty similar, pretty trivial, and pretty simple theorems in regards to even odd functions and the properties of integration. So that's just good to know. It's a good refresher to have with the, this algebraic and function properties and then the integration properties here. So now let's go ahead and move into something more complicated, which I will do in just 1 second. Okay, so now what I want to talk about is actually going to be a useful sum. So what I mean by useful sum is that we're going to define some summation, and we're going to find some properties of that summation. So the first thing I want to show is let's just see a summation, a simple summation, which is going to be, let's just say a summation from k being equal to 0 all the way to some value n. And we're just going to be summing up these values of k. So when we sum up these values of k, what we're doing is we're essentially starting with 0. So 0 plus, when we're not going to include that because it's 0. So 1 plus, and then 2 plus, 3 plus, all the way to whatever the value of n is. And we'll keep doing that for all values of n. So similarly, we also have the summation, let's just say, of k equal to 0 to n, but now rather than k to the first, which is k, we'll do k to the second, or k squared. And that's just going to be 1 plus 4 plus 9 plus n squared. And then similarly, last one, k cubed instead of k squared. And that's just going to be 1 plus 8 plus 27 plus all the way to n cubed. Okay? And then one last one I want to actually implement or show is just k equal to 0 for n, but k to the 0. But k to the 0 is simply going to be 1. So we can write 1 here. And so we're summing up 1 n number of times, so which is simply n. So that's that. And this is the same thing as saying k to the 0. Okay? So now why did I introduce this? Well, I want to show you some general equation or general form that can get these values or these summations without actually taking a summation. So I will introduce these as fact, and then we'll go ahead and actually show them, show an algebraic proof for all of them for this one, which we've already showed, and then k with the power being 1 and the power being 2. And for an exercise left to the audience, you can do k to 3. It's similar. You'll see how the process works as we introduce the topic. So what I want to introduce here is just an equation to find, given some value n, to find the summation, or the value of the summation. So for k being equal to 1, or for the k being raised to the first, we'll have this equation of n times n plus 1 divided by 2. Similarly, for k raised to the second power, we'll do n plus 1, 2n plus 1 divided by 6. And then finally, for k cubed, we'll have n plus 1 squared, and that's squared. Okay. And a quick demonstration of why this is true. I would compute, let's just say this one, for n equal to 3. So for when n equals to 3, what we can see is that we're just summing up 1 plus 2 plus 3, which is 6. And using this equation, we can see the same thing. This is 3 times 4 divided by 2, which is 6, right? And then again, we can show the same thing for this. N equals 3. So that's going to be 1 plus 4, which is 5, plus 9, which is 14. So 14 is what we're looking for, okay? So when we do this, we just do 3 times 4 times 7, and then divided by 6. So this is 12. So 12 divided by 6 is 2. So 2 times 7, which is 14. All right? So that's 14. Finally, we can solve the same thing for n equals 2 in this case. I can do larger terms like n equals 3, but for the sake of time, just for the sake of making sure this is quick, I'll just do n equals 2. So in this case, we'll just have 2 times 3 over 2 squared. These cancel, the 2's cancel. So we're just left with 3 squared, which is 9, which is exactly what we're looking for these first two terms. Since we're computing at n equals 2, 1 plus 8 is in fact 9. Okay? So you can prove this, you can show this for more examples, for more values of n if you want to show, when k is raised to the first, show it for the first 5 or 10 or whatever it might be, which is also very simple. Let's just say we want to do, let's just say for, when n is 10, it's going to be 10 times 11. 10 times 11 is simply 110. Divided by 2 is 55, right? And then you can show that if you want to do the actual mathematics and or the actual computation in a 1 plus 2 plus 3 all the way to plus 10, and you can show it's equal to 55. So now this isn't a proof. This is just an example of this definition. But I want to actually introduce a recursive formula to compute these. So the proof is beyond the scope of this class, and you can go look at it. It's not actually a very complicated proof, but it is beyond the scope of this class. So I'm not going to discuss it too heavily. But what I will do is I'll quickly introduce a notation, or for a function essentially, which is just going to be s of n comma I. So some function s with the values n and I, and that's just going to be equal to summation from k equals 0 to that value n, which is from here, of, let's say, k to the I. So we can see, actually, that all of these summations here are in that form. So, for this first one, for example, it's s of n comma 1, because we're going to the end, our summation is ending at n, and we're raising k to the first. And similarly, s of n comma 2, and s of n comma 3, and then s of n comma 0 in this case. And s of n comma 0 is what we'll actually consider a base case for later. And once again, s of n comma 0 is equal to n, because it's just multiplying 1 n times. Okay? So now, with this notation, I want to introduce a general form for finding these formulas that we've given here. And we're going to use that, we're going to do this recursively. So we're going to define some recursive function that will do this for us. Okay? Okay. So I want to define this function, s of n comma I, which is just going to be simply 1, I plus 1, n plus 1, to the I plus 1, minus the summation from j equal to 0 to I minus 1, and then I plus 1 choose j, and this is the recursive part, s of n comma j, like that. So we're dividing this entire thing by I plus 1, and we're doing n plus 1 raised to the I plus 1, subtracting 1, and then subtracting the summation. And keep in mind this binomial coefficient here that we're using, or this choosing operator, is going to be the combinations of all the ways we can do I plus 1 with j elements. So generally speaking, this is just going to be defined as, and generally if it's n choose r, this is just going to be n factorial over r factorial n minus r factorial. Okay, so that's what this that's what that means. Okay, so that's the general formula. So now I wanted to show this. So we're not proving this in this class because once again it's beyond the scope. But I do want to quickly just show this is true for both. Let's just do I equal to 1 and I equal to 2. So for when I equal to 1, we'll just do s of n comma 1. And we're just going to do this formula as it is. So 1 over 2 n plus 1 raised to the 2 minus 1 minus 0, or j equal to 0, 2, 0 of 2 choose 0, or 2 choose j, s of n comma j. And we can see that when we're summing from 0 to 0, this is simply the sum of when we're summing from 0 to 0, this is only just going to be j when j is 0. So there's only one element in the summation. So we can just do 2 choose 0, and then s of n 0. So we can notice, first of all, that we've already defined this base case s of n comma 0, which is just n. So we can write this as n. And then simply, once again, 2 choose 0 is going to be 2 factorial divided by 0 factorial times 2, or 0 factorial times 2 factorial, which on the denominator, which is simply going to be 2 factorial over 2 factorial, which is just 1. So this is equal to 1. Another way of thinking about it conceptually is if you have two elements and you're trying to pick the zero unique ways to pick them, you're only going to be able to pick that in one way because you're picking 0 elements. So this is equal to 1. So this entire piece here is simply equal to n. So if I continue this math, we'll just do n squared plus 2n plus 1 minus 1, because this here, minus n. And that's simply going to be, these will cancel, and then this 2 will go away. And it's going to be simply 1 over 2 n squared plus n, which is equal to n plus 1 over 2. And yeah, so there you go. That's actually exactly what we had before when we showed this, when I treated it as fact. But now we've actually shown using this recursive formula, but that's what it is for the summation of k to the first from 0 to n. So now what I'll do is actually I'll write this out here, that s of n comma 1 is equal to n plus 1 over 2. It's a little bit close, but I will just box this. Okay. So now what I want to do is I want to show the same thing, and okay. So I want to show the same thing, but now instead of I being equal to 1, I'll show it for I being equal to 2. So s of n comma 2 is going to be simply equal to 1 over 3 n plus 1 cubed minus 1, and then 1 equal to 0, 3 j s of n comma j. And then we'll continue 1 over 3. I will just expand this here. Oh, sorry. And then minus 1, and then minus this summation here. So our first, so we're summing up from 0 to 1, so we'll have two terms. The first term is going to be 0, which we had exactly before. So 3 choose 0 is simply going to be 1, and then s of n comma j, or when j is 0, is simply going to be n. So we've already discussed this before. This is just n, or this is just n. And I'll put a little bracket here because we are subtracting this entire summation. So we want to make sure we distribute the negative sign later on. And then our second summation is just going to be 3 choose 1. 3 choose 1 is simply 3. And then we'll have s of n comma 1, which we have from here. And s of n comma 1 is just, and I'll actually erase this. S of n comma 1 is n times n plus 1 over 2. So we'll have 3n, n plus 1 over 2 as the last term here. Okay? We'll continue onwards. So 1 over 3. And then we can see that these will cancel. So we'll have n cubed plus 3n squared plus 3n. And then we'll just do minus n, and we'll distribute the negative sign in, minus, and then we'll actually also distribute this 3n. So 3n squared plus 3n divided by 2. Okay? And we'll also want to make sure that we distribute this negative sign in later on. Okay. So really quickly, I'll move over here to finish this off, but we can show, what I'll do is I'll multiply this entire bit here. Well, first of all, we can see that 3n minus n is just 2n. And then I'll multiply this entire piece here by 2. So we have 2n cubed plus 3n squared, or plus 6n squared plus 4n, and then I'll divide the entire thing by 2. That way we have a common denominator, and then we can add these, add and subtract these together. So that's going to be simply 2n cubed plus 6n squared plus 4n, and then minus 3n squared minus 3n, all divided by 2. And then what we'll do is actually move this 1 over 3 in. So we have divided by 6. Okay? And then lastly, I'll use this bottom line here. We're going to have this equal to, we're going to have 2n cubed plus 3n squared, because this 6 and this 3 here will subtract, plus n. And that's n because 4n minus 3n. And then we'll divide this entire thing by 6. And then using some simplifications and some factorization, we can quickly just see that this is actually equivalent to n plus 1, 2n plus 1 divided by 6, which is exactly what we showed before. So what we've noted is that we can find these general formulas for these summations just by using the previous summation, right? So for the case of when we needed to have s of n comma 2, which we just did, we needed to have s of n comma 1 and s of n comma 0. And to do s of n comma 1, we needed s of n comma 0. So if we kept going and we wanted to do s of n comma 7 or 8 or 9, we would just need the preceding s of n commas. So s of n comma 0, 1, 2, all the way to whatever that number is, minus 1. And we can see that's exactly what the summation does. When we're doing I minus 1, it's simply what power that we're raising k to, but it's subtracting 1. And that should make sense intuitively as to why we need 0 to 1 and 2 and 3. And that's why it's a recursive formula, because we're using the previous term. So similar to Fibonacci, uses previous terms to produce more terms. All right, so that is that, and that's actually the conclusion of this part of the lecture. We're currently 28 minutes into the lecture, and I'm going to introduce our second topic for the day, and that's the last topic I'll be going over. It also corresponds to a useful sum that we can have. The general formula is also recursive. Okay, so now that we have that previous s of n comma I defined as a recursive formula, let's also introduce another recursive formula we can use that's very, very similar to the previous one. So we're going to define this formula very simply as t of n comma j comma x. And that's going to be the summation for k equal to 1 to n of k to the j and then x to the k. So it's very similar to our previous formula, except now we have a component x to the k, and we also start our lower bound at 1. So let me write out our previous formula. And this one is k to the 0, like this, to n, with k to the j. And I want to note real quick is that at k equal to 0, when we evaluate this first term of the series, or the first term of the sum, well, we're only doing 0 to the j. So for any finite value j, it's actually just going to be 0. So what we can do is we can also say that this is the same thing as k equal to 1 of n, and then k raised to the j. And we'll use this in a second. So now I want to take this formula and I want to show you can relate it to this formula here. So if I do t of n j 1, So where x is 1, we're holding x steady at 1. And then we sum from k equal to 1 to n. Well, now we're going to get k to the j, like we expect. But then we have our x value being 1, which is raised to the k. And for any finite value k, our value of 1 raised to that k is going to just be 1. So this is simply k equal to 1 to n of k to the j. So these two are actually equivalent. So you can say that s of n comma j is the same as t of n comma j comma 1, because we're only introducing this one x to the k component here, which we can remove if x is 1. Okay? So with that, I also want to take the derivative of t of n comma j comma x. Okay? And we're going to multiply the derivative by x. So that's kind of confusing as to why, but we'll see why that makes sense in just 1 second. So if we take the derivative, so x, so we're multiplying this entire derivative. Actually, yeah, I will remove that for a second. So we're just going to take the derivative simply of this right there. So we're going to do d of dx t of n j x, which is equal to the derivative with respect to x of the summation k equal to 1 to n k to the j and then x to the k. And so we'll notice that this summation is just the same thing as this sum and this derivative are interchangeable because the derivative acting on multiple sums is the individual derivatives added together. So we can say in this case here, we'll continue our summation k equal to 1 to n, and k to the j is a coefficient, so we're not going to do anything to it. That's just k to the j. And then x to the k will simply become k times x to the k minus 1, just by the power rule, where we'll take the power, multiply it by that, and then subtract 1 from the power, which is why we get this. So now what we can do is we can just quickly see that this is the same thing as saying k equal to 1 to n, and we'll move this k into this power. So it's in k to the j plus 1. And then we have x to the k minus 1. So now you'll see, this is actually very similar to this formula here. But only the change is that now j is actually j plus 1. Issue is, we're now missing one factor of x, or whatever you want to call it, from this term here. So what we can simply do is we can multiply this entire thing by x. So if I multiply this if we multiply x into this, we'll simply get, for every single term, since x is a constant in respect to k, we'll simply get x to the j plus 1 and then x to the k, which is exactly the form that we were looking for from here, with the only change being that now j is equal to j plus 1. So what we can say here is that this is actually equivalent to t of n j plus 1 to the x. Okay? So now this is the, with j being 1 greater, this is the formula, and it's simply just equal to So what this says is that if you want to calculate for any value j, if you want, let's say, tn comma 3 comma x, well, what you'll do is you'll simply take x times the derivative of tn with parameters n, j being 2, which is, because this is j being 2 here, but it's now j plus 1 is 3. But I can write that out real quick. So let's just say t of n comma 3 comma x is equal to x derivative of t n and then 2. So this is the recursive formula. This is how we know it's a recursive formula, because computing any term for tn j plus 1 comma x will require the previous term or the previous j. If that makes sense. I hope that makes sense. So we can actually use that in an example. So I'll quickly just erase this and I'll write this formula once again elsewhere. Next, I want to show a quick example with a specific example for t of n, j, and x. So if we have, let's just say in this case we want j to equal 1. So we have n comma 1 comma x, which is simply the summation from k equal 1 to n. But now k is being raised to the, oh my bad, this is actually going to be 0. So now k is being raised to the 0th power. K to any number to any 0th power will be simply, or any finite value to the 0 power is going to be 1, and we'll just have x to the k remaining. And I can actually show a similar version of x to the k with this series with some algebraic manipulation. So let's just take 1 minus x times, and this is the coefficient, k equal to 0 to n of x to the k. Well, what we can say is that we can just move this term here, the coefficient, in. So that's just going to be k equal to 0 of n, 1 minus x, x to the k, which is the series k equal to 0 to n, x to the k, minus x to the k plus 1. And we're doing k plus 1 because we're taking x, multiplying it by x to the k, so it causes 1 additional in the power, which is where we get that from. And we can approach this like a telescoping series, actually. And what I mean by that is that when we have k equal to 0, our initial case, what we'll have simply is the first term will just be 1 minus x, because now it's 0 plus 1, or x for the first. And we can continue the series So there are additional terms between here, hence the dots. I could have spaced that out, but I hope you can make it out. But essentially what I show here is that for every term there's a negative x, or a negative value, and the first term of the next sum, or the first term of the next term, is the positive version of that value. So these two cancel out. And that keeps happening all the way until we also cancel out this last term here. So the only terms remaining are the first term in the entire sum and the last term in the entire sum, which is simply going to be 1 minus x to the n plus 1. So I'll erase this, and I'll just write that here. 1 minus x to the n plus 1. Okay, so that's what that series is equal to. And if I want to get this series alone, I can quickly just show k equal to 0 to n, x to the k, and I'll just divide both sides by 1 minus x, okay? So we'll get 1 minus x to the n plus 1, and then 1 minus x. So this is a series for x to the k. Now I want to show you that this is a series for x to the k. The only difference is that this is for k equal to 1 to n. This is k equal to 0 to n. Well, very simply, we can actually show you that the series from k equal to 0 to n is just an additional term for the, on top of this series from k equal to 1 to n. Starting from 1 to n, it's just not including 0. So what we can do is just remove the 0 term from this case. So x to the 0 is simply 1, so we can just subtract 1 and then change this bound from k equal to 1, and those are equivalent. So now we know that this is actually equal for t n comma 0 comma x. Okay? Now, what we can do with what we've just found here is we can actually start computing this here, because now we have a value of tn, 0, x. So if we wanted to, we can just take this derivative of that, multiply by x, and now we will actually get what this is, which is for j plus 1, in this case our j is 0. So j plus 1 will be 1. So we'll be able to compute t with parameters n, 1, and x. So we'll do that here. So t of n, 1, x is x d over dx of t of n, 0, x. And we have t of n, 0, x there. So we can quickly just put that in. Like so. Okay, so I will quickly just erase this side here, because we no longer need it. But I will keep, actually no, I don't need anything here. Okay, so we can quickly just note that the derivative of -1 is this is not important, because the derivative of -1 is just 0, so nothing changes there. So we're taking the derivative of that, which is, we can quickly do that just by doing the quotient rule. So the quotient rule in this case is, and we're going to leave x out for now. It complicates the process if we want to introduce it later. All right, it makes it more complicated if we introduce it now. We can simplify it by doing it later. So I'll start it up here, our derivative for just this, and we'll multiply x into this later. So we can simply just take the value of the denominator and the derivative of the numerator. The derivative of the numerator is simply negative n plus 1, and then x to the n. Because we're taking the derivative of this, well, the derivative of 1 is just 0, so it's not important. We didn't have a negative. We take the power down, which is n plus 1, and then we subtract 1 from the power, which is x to the n. Okay? And then we subtract the value from the numerator, and then the derivative of the denominator, which is -1, like that. And then we divide all of that by 1 minus x squared. Okay. So that is that. Now what we can do is we can start doing some manipulation with the algebra. Okay. So first of all, what I'm going to do here is just a quick simplification. We have a -1 here, so I can actually just make this a plus sign, like that, and I can remove that, just like that, if that makes sense. So we're now doing just we just have to simplify this. So this is the derivative. Now we just want to make a simplification of this. Okay. So we can quickly just say we can move out this negative term. So we'll have on this numerator we'll have -1 minus x, n plus 1 times x to the n, and then we're just going to add 1 minus x to the n plus 1, like that. And let me just divide the entire thing by 1 minus x squared, like that. Okay. So now we can take this one more time. We can do we can actually now incorporate these terms together. So that's just going to be, we'll leave a negative out here. So 1 minus n is just going to, or 1 times n is n, and then 1 times 1 is plus 1, and then negative x times n is negative xn. So I'll just write negative nx because it's a coefficient, and then negative x times 1 is minus x, like so. And then once again we have the negative sign out there. We have x to the n plus 1 minus x to the 1 minus x to n plus 1. Okay. And once again, this is only the derivative of this bit here. You still have to multiply by x at the end, but I need the space here. So we're going to bring this out over here. And obviously this entire thing is divided by 1 minus x squared. So over here, we can quickly show that when we can multiply these factors in. So we'll have negative, and actually really quickly, so we'll just do, so we'll do negative x to the n plus x to the n minus nx to the n plus 1, because we're multiplying negative nx times x to the n, and then minus x to the n plus 1. And then we'll just subtract, or add 1 minus x to the n plus 1, like right here. Okay? And now what we'll do here is really quickly, we need to distribute this negative sign in. So we can do that really quickly. Negative x to the n minus x to the n plus nx to the n plus 1. And obviously, cannot forget the denominator. Very important. So once again, negative x to the n minus x to the n plus nx to the n plus 1 plus x to the n plus 1 plus 1, I'll just use this one here, minus x to the n plus 1 over 1 minus x squared. Okay, so continuing onwards, we can just see trivially that these two terms will cancel. And then what we'll do is we'll just quickly do this as well. So we'll just move 1 out to the end because it's positive. 1 plus nx to the n plus 1, like so, minus x to the, or minus n to the x to the n, so that's that, that's that, that's that, and then minus x to the n. So that's a simplified form of the derivative. We can obviously, well, we can't actually pull out much from here, but what we can do is now we can't forget that we have to multiply this by x because of this x that's here. So we'll multiply this entire thing by x, and we can just get x to the n to the x plus 2 minus n to the x n plus 1 minus x to the n plus 1 all over 1 minus x squared, like that. And then one more thing I would like to simplify here before we move on is just going to be here. So we have x plus nx to the n plus 2. And we notice that these terms, this x to the n plus 1 and x to the n plus 1, are the same actually. So what we can do is we can subtract, and then I'm going to pull out an x plus n to the n plus, or x to the n plus 1, and then we're just going to be left with n plus 1, like so. And we're doing n plus 1 because when if we're distributing the negative sign, this is the same thing as having that, if that makes sense. So then that's the numerator, and we can swap this around so that we have like so, and then we just divide that by 1 minus x squared. So I want to show you that this is actually the equivalent. This is the formula for t of n 1 and x, because we derived this from the case of the formula for when j was 0. So now j is 1 because we can show that we can get the next j, 1 added onto j, just by taking the derivative and multiplying by x, which is exactly what we've done here. So this is the same formula, okay? Now, I did want to show, and so this is the formula here. And so I can erase this real quick. So remember, I did say before that t of n 1 1, or I did say that, and this is an example, so we finished that, we have shown, and this is also an example, we have shown the formula for t with parameters n, 1, and x. So now we also know this, that for the t with parameters n, j, and 1, it's equivalent, it's equal to the s of with parameters n and j. So if we wanted to find the series for when we're doing the summation from 0 to n of only k and k raised to the first, well, we can just do that by doing 2n 1 equals s n 1. And these are the same thing, okay? So basically what we need to do is we're basically evaluating this, or we're finding what value it approaches, and this is a hint, you know, at that x value of 1. So let's just do that. We can actually do that very simply. So it's going to be, and we can quickly show, we can't just put this in because 1 minus x with 1 minus x with x equal to 1 is just 0. 0 squared is 0. Divide by 0 is a divide by 0, which you can't do. So what we'll do instead, we'll just apply the limit. So the limit as x goes to 1 of x to the n plus x plus n plus 2 minus n plus 1 n plus 1, and then 1 minus x squared. Okay. And I'm going to erase this real quick because it's written again here, and I want the space. Okay. Okay. So I'm going to apply L'Hopital's rule because this is going to be problematic for us because we're dividing it by 0, and the numerator is also equivalent to 0, and we can show that. It's pretty easy to show, so I'm not going to show it, but you can show it yourself. It's equal to 0 over 0. So obviously I don't want 0 over 0, so we're going to apply L'Hopital's rule. I'm not going to use any special notation to show that I'm applying it, but simply we'll get 1 plus and so this is actually just still going to be, it will still be 0 over 0. So we're going to do it again. So over here, we'll just show, we'll take the derivative one more time. So we're going to do 1 plus, now we're going to do n, and sorry, my apologies. The derivative of 1 is just 1, or the derivative of 1 is 0. So n plus 1, n plus 2 of x to the n, minus what looks like n plus 1 squared of x to the n minus 1, with the denominator being, and you can rewrite this as negative 2 plus 2x, or 2x minus 2. So now this, the derivative of that is just simply going to be 2. And so we can see, so this is just 2, the derivative of this is 2, and we can see that actually, I forgot to write my limit notation here, but that's the limit as x approaches 1, and this is the limit as x approaches 1 as well. So we can write, finally here, we can evaluate this as 0, and I'm not going to show all of the algebra because that's extraneous. You already got to this point where you can now, this is over 2, so this is actually going to have some value, and it's going to be in terms of n. And this is simply going to be n plus 1 divided by 2, which is exactly equal to s of n comma 1, like we showed earlier in the lecture. So we've now shown that both s of n comma j and t of n comma j comma x can be used to find these formulas. And these are extremely useful later on in financial mathematics. But now we've only covered like the pure mathematics part of it, so we've yet to discover a lot of these concepts. But this is a really interesting and really fascinating facet of mathematics, that you can have these generating functions that are recursive to generate these to get the sums, to get a general formula for the sums, from some bound to some other bound of all of the the natural numbers k. Well, including 0, so integers. So yeah, I hope you guys enjoyed the first lecture. In the next lecture, we'll be covering sequences that are following linear recursion, and then we'll also be talking about determinants and a little bit of linear algebra in that lecture, which should be significantly shorter, just due to the nature of the content. So that's all for this lecture, and I will see you in the next one.